Okay, so the question was on summary 4. Again, you're gonna read a couple papers. One's gonna be on geothermal, one's gonna be on wind, and hopefully the ones you're reading have some quantitative information in there in terms of this is the rate at which energy is going to come out of both of your systems. This is what it's going to cost you to put the thing in up front. This is what the value of energy is in the long run, and here's kind of your payback period. So, yeah, I would like you to say here's the upshot of paper 1, little equation or some numbers. Here's the upshot of paper number 2, equation, numbers, and then just get those two talking to each other into this little comparative model that I'm going to show you here. So, does that answer kind of question? Okay. So I started this. Okay, I called it summary for time value. And this is going to be good practice when you take ETEC 214, energy storage and distribution, because energy storage and distribution is all about integration as well. You know, you've got some rancher, and we'll think of the Hull's Dairy. I don't know if you guys have visited there yet or not, but Hull's Dairy is able. It's a very unique technology, so it's kind of always moving forward and backward and fits and starts. But unlimited, vast amounts of cow manure, sort of building up. What do you do with it? Well, you could sell it as manure, as compost. You could throw it right on the ground somewhere and enhance the soil, or you could make electricity with it. In fact, that's what they're doing. So they're taking all the cow poo, sort of shoveling it down into a couple bins. The solids go down, the liquids come up. It's then pumped into a large tank where anaerobic bacteria go to work on it, turn into biogas, and then that biogas is burned in a V8 engine and turned into electricity through a generator. So, you sit down and say, gosh, what's that tank cost? What's the motor cost? What's the maintenance cost? And then is it really worth it? Why don't I just go ahead and buy coal-fired power plant electricity instead? Why go to all this trouble? So that's where every renewable energy technology goes eventually. And in fact, it's even where nuclear versus coal goes. All of these technologies are competing with each other. Hydro, you name it. So let's take a look. So what I did, I started out with a little spreadsheet that we've been working on for 214, and there are, at least in a very simple way, 3 fundamental functions for money, and I want to make sure I don't get this backwards. F, A, P, A, F, P, P, F. Engineering economics and economic design. Let's just take a quick little look at this. Let's get a new one. I want to find the because what this is, F is future, A is annuity, P is present, and I think I might have winged it last time. I want to make sure I get these right. Let's go to Wikipedia. Or not. Yeah, there's present value, there's future value. It's just the notation. Well, let's look at this very first one. So if you're given the present value, and I is positive, and it will be. I is the interest rate. It's just some number, 0.1%, 10%, what have you. You can see that the future value will always be greater than the present value. So let's go back into our spreadsheet, and let's put in, yeah, okay, here you go. So the letter in the numerator is what you're getting, and the letter in the denominator is what you're putting in. So another way to think of it is kind of like this: f as a function of p, right? So if you know p, you're going to get f. And in this case, the AMT is serving all three roles. It's serving the role of A, which is the annuity, the role of P, which is the present, or the role of F, which is the future. And all it's doing is putting A, F, and P in all 6 permutations. There's only 6 ways to combine those 2 letters. So this one here is showing the present value as a function of the future value. This is saying if I know the future value, $1,000, and I'm going to get 10% in 2 years, I better put in $826.45 right now. So okay, so that's that. Now, what I'd like to do here, I made a little bit of progress here, and I think maybe the best way to do this, let's just grab these cells, let's just shove them over here for the time being, and we'll have the cost. The initial cost is going to be $3 million, let's just say for on average. And now here's what I'd also like you guys to do. We did this exact same thing when we put in our CRELF proposals last year. So CRELF is the CLES Revolving Loan Fund, and we actually got 2 of them funded, not fully but partially. So it was the first time we ever had like a 2. It was pretty cool. So it's a sign, I think, of good things to come. But the thing to think about in your energy tech project is the dollars per watt. So you're going to install a 3 megawatt system. What's the dollars per watt? If it's $3 a watt, it's going to cost you $9 billion. If it's $5 a watt, 15 million, etc. So same thing with your geothermal. How many watts is this thing going to pump out? Same thing with your wind. How many watts is it going to pump out? So to compare apples and apples, you just want to put it in dollars per watt. That's the power. And then you're going to go in and that'll be the capacity, what's the maximum flow. With geothermal, you can pretty much count on the same flow continuously. Ground temperature isn't changing much throughout the season. With wind, it's going to change season to season. You might, get a lot more wind in the spring and fall, not so much in the dead of winter or the dead of summer, right? It's just kind of the way the wind blows. But the problem there is you're like, well, gosh, I'm going to need, if I'm running, let's say, my air conditioner or my refrigerator, I'm going to need that wind power when it's not actually blowing. I'm going to need it in the summer. So you're going to have to kind of think of it in those terms. I don't expect you to do a day-by-day analysis, but just sort of, mention that in your write-up, saying, here's how much wind I think I might get over the course of a year. Here's my electricity demand over the course of a year. Do I come out behind? Do I come out even? When do I break even, basically? So let's do this. I want to swap oops. Insert. All right. Let's do that. Let's take that. There's my upfront capital cost. Here are the years of the project. I'll take those guys, slide them over here. I'll get rid of this. Shift them left. Okay, fine. And this is going to be I'll just call it ROI, return on investment, and I'll call this ROI cumulative. This is just going to be the year. Okay, so I'm going to grab all four of these, and I'll show you where these numbers came from. I'm jumping the gun a little bit here, but I'll show you where they came from. So I'm going to insert charts, and I like to use the chart with without the interpolation. In this case, it doesn't really matter because I'm just looking at straight lines. But I like just so, because otherwise you don't really know what that interpolation function is that Excel's doing. For summary 3, remember we put in linear, we put in parabolic, we put in exponential. In this case, it's just each dot gets connected by a line. There's no funny curve in between they're trying to interpolate for you. So just use the chart form I showed. Okay, so just to get back to this, the return on investment that we were looking at for this particular case, kilowatt hours per year. Yeah, so I just made something up where I had a 1 megawatt system. This is probably a little big. Let me go in here. Insert. And I'm just going to go ahead and do a wind and a geothermal while we're in here. And let's maybe just back it off a little bit to maybe the residential scale. So I think instead of dealing with $3 million, let's just call this 30,000. And this equals that. And what I'm going to do is pin that number right here and then just drag it down. So I've got 30,000 bucks. Now, let's think about this for a second. This is a slightly unconventional way to plot this, but for me it works really well because it says I put in 30,000 bucks. Actually, when did I put that in? I actually put it in year 0. And let's see if I can now tweak each one of these graphs. Okay, so I don't know if you guys have seen this in Excel before, but you can actually go in, drag that up, take this guy, drag it up, take this, Control C, copy, Control V, paste. The reason I went for Y0 is because you're putting the money in right now. Year one happens a year from now. Okay, and then this guy, what I'm trying to do right now is just distance myself from this little cell where I think it's a little big for what we're typically discussing. Insert, and also another thing, just to validate what I'm doing here. I've got a board of energy technologists around the state, and every time I ask them, what do you need our grads to be doing? They're like, well, to crunch some numbers and spreadsheets. So once you get a hold of this and get rocking on it, it'll be a very valuable skill for you down the road. Okay, so now let's just say for wind, let's do it this way, and here's going to be geothermal. And let's just go ahead and put in dollars per watt for both of them. So we spent the last several lectures going over performance characteristics of wind systems, and I would say a reasonable cost for a wind system installed would be about $5. Actually, that's relatively cheap, but let's just go ahead and put that in there. So Control 1. Currency, $5, okay. Geothermal, let's just say for the sake of argument it's more expensive. Let's put it in at $10. Control 1. Currency, okay. So there's dollars per watt. Control U, underline that guy. Get these all squared away. Now size, and we'll just put this in watts. And let's just say we're going to put in a 10 kilowatt system. 10,000 watts. Do a Control 1. I really like seeing the numbers there with a comma in them. 10,000 watts. Geothermal. Let's take one quick crack at the concept of enthalpy before we get too far down. So just keep this little block in mind, and I want to discuss like geothermal in physical terms before we do this calculation. So let me just run through this kind of quickly. So geothermal. What we're looking at is enthalpy. Looks a little bit like energy, sounds a little bit like entropy. Let's go out to the engineering toolbox and look at the definition. So you can already see it's thermodynamic potential, internal. Oh, there's even a neat little Khan Academy. I might, if you want to just, sitting around after dinner, I would check that guy out too. All I'm really looking for here are the units. Okay. Now, in this case, the internal energy is just going to be the heat value. It doesn't include any chemistry. The pressure times volume if in fact you were getting pressure out of your geothermal system, you would have something there, but there's no real pressure. Everything's kind of an atmospheric pressure. But let's just kick out to the internal energy too. So the point is, it's just enthalpy has units of energy. It's not some other weird thing. It's just energy. It's same dimensions. It's measured in joules, kilograms times meters squared per second squared. Now, here's what it says. Excluding the kinetic energy of motion of the system. Now, so that's why it's somewhat different from the wind system, because in the wind you've got the kinetic energy, the wind blowing through it. In the geothermal, you just got the thermal energy of whatever's in the earth. See if there's anything else worth noting here. Not so much. Okay, so we're just going to treat the enthalpy as it's written as H equals U plus PV. We're going to ignore PV for now, and we're just going to call U equal to Q equals C sub P M delta T, or Q dot. So the heat flow rate. This is the power of the system. It's how powerful it is. So this is actually in watts. It's in watts of heat transfer to the system. Q dot equals C sub P M dot. So that is the rate at which fluid flows to the system. Now, typically in your geothermal, you're just going to have water flowing through the system. So you just have to know how many kilograms per second flow through the system, and then you're going to have some delta T. So let's look up values for each of those, and then we can get the enthalpy flow rate in the geothermal. We can figure out how powerful it is, and then we'll sort of know the amount of energy we're getting from the system. This is the most fun I've had all day. I'm serious. Okay. Specific heat of water. 4.6 or 4.1. Let's just call it 4.2 joules per gram. So C sub P equals 4.2 joules per gram. M dot, we're going to have to come up with. How you'll look at a pump, you'll see, how many gallons per minute. You'll have to convert that to kilograms per second. So let me go ahead and write that. In fact, let me write it here. So we know that the units of C sub P, the units are joules per kilogram per Kelvin, or per Celsius. Doesn't matter. One change of 1 degree Kelvin equals one change of 1 degree Celsius. The units of M dot are going to be kilograms per second, and the units of delta T, of course, are just kelvins. So now if we just do a quick little unit analysis, we can see that the units of Q dot, the power of your geothermal system, equals joules per kilogram. So I'm just going to multiply these guys times Kelvin times kilograms per second times kelvins. The kelvins disappear, the kilograms disappear, and you're just left with joules per seconds, and you're left with watts. So this is how we're going to compare apples to apples in our geothermal versus our wind. Let me get back to my spreadsheet, and that brings us right to this one little cell. What's the power of the system? So, you know, I'm in whatever papers you pick up, you know, there are a lot of different types of geothermal technologies, but every single one of them, you know, more than likely it's using water. If not, you'll just have to figure out what the specific heat of glycol. Maybe it's using air, and then it's just like much smaller heat capacity, but whatever it is, it's going to have some number, some CCP. Your pump is going to have some capacity, kilograms per second. You might need to convert gallons per minute to kilograms per second. That's just units conversion. And then your delta T, that's a little trickier because the delta T is going to change as a function of time of year, right? So let's look at what delta T is going to look like for the geothermal. So here is ground temperature, constant, 52, let's just say, degrees Fahrenheit over the course of the year. Your, I'm going to make this super simple. Your heat profile is going to look something like this. So I'm going to call this March, April, May, June, July, August, September. Let's see, 1, 2, 3, 4, 5, 6, 7, close enough. October, November, December, January, February, March again, right? So, and again, it's super simple. I've just drawn a sine wave is all I've drawn. And I'm just assuming that the temperature in March at time 0 equals the temperature in March at time 1 year, and that, you know, as we sort of pass through the equinoxes, the temperatures are about the same, right? So it's about the same temperature in September as it is in March. It's cold, or it's hot in June, July, August, and it's cold in December, January, February. So it's not a perfect model, but you can see that right here, Q dot is sort of maximized because this, well, let's draw it this way. This is your delta T right here. So in the summer, since the ground temperature is colder than the air temperature, you're pumping cold. In the winter, since the ground temperature is warmer than the air temperature, you're pumping heat. When it's September and March, you're not doing anything because everything's the same temperature. And maybe one thing, yeah, I think you guys could do this. I think you could do this. Let's just do it this way. 0, 1. Oh, Microsoft Excel. You could get up to 12 months. And then let's see here, you could go ahead and say equals that see if I can do this on the fly, times 2 times pi over 12. Equals sine plot a sine wave. So in this case, what you could do is each of these numbers is basically your delta t. So again, if you don't want to go down this rabbit hole, you don't have to. I'm not going to require it. But let's just say the geothermal, you're going to run a 12 kilowatt system. Now, the 12 kilowatt system is more or less going to be this sort of maximum value. I mean, it's like kind of the maximum amount of power it could run. So obviously, in these other 2 months, March, September, and March again, you're not going to run anything. So what you could also do is this. Equals average. You just average that sine wave. I think the bookends are messing it up. Let's just get rid of the 0 and the tiny number. 46. Oh, I know what the problem. That's true. The average of sine is 0. We just want to do a half wave. Hello. There we go. Okay. So that's more or less, you might think of that as like the RMS value. Okay. So 0.5 is sort of your average heat. So you could take this, in fact, let's do that. Size. So here's your coefficient of performance. So your wind turbine is not going to be running 10,000 watts 24/7, 365. It might run 25% of the time if you're lucky. Geothermal, we take a look at this, and when you take NRGY 235 or John Freer's CSTN 283, we talk about what are called heating degree days, sort of how many total, like, sort of, for example, if you need to keep your house 1 degree warmer than it is outside, that's 1 heating degree day. For 1 day, that's 1 heating degree day. If you need to keep your house 10 degrees warmer out than it is outside for 10 days in a row, that's 100 heating degree days. So that's more or less what you're dealing with in your geothermal. Coefficient of performance, I'm just going to take that average of that sine and call it 0.553, because that's about where I am. I'm never really at 1, I'm never really at 0, I'm somewhere in between. Well, sometimes I'm at 1, but sometimes at 0, but rarely exactly either. So equals that number. Okay, so there's your coefficient of performance. Control 1, let's just get them both to a number. Let's let their significant digits match. Fine, okay. And this is going to be power AV in watts. So now this equals the size times coefficient of performance. On average, you're going to make 2,500 watts from your turbine, and you're going to make that many watts from your geothermal. And again, this is an annual average. Now you're going to get dollars per watt. Now let's call it out. So this is sort of, dollars per watt for the what's called the nameplate capacity, and this is the dollar per watt out equals dollars per watt times watts. Let's see, did I do that right? No, this is just dollars. Sorry, it's just dollars. No, that is dollars per watt. What we need to do here, let me just sneak this in. Insert, shift and right. This is just dollars. This is how much the thing costs. Equals dollars per watt times this guy. There we go. So your 10 kilowatt wind system is going to cost you 50 grand. Your 12 kilowatt geothermal is going to cost you 120 grand. But on average, it's still not right. Power. Oh, here, I know how to do it. Equals dollars per watt. There we go. There we go. Okay, so we had a certain dollars per watt of the nameplate of the system. You bought a 10 kilowatt turbine, it cost you 50 grand. You bought a 12 kilowatt geothermal, it cost you 120 grand. But since they're not always operating at full capacity, let's turn that into currency. This is really what you paid. You really paid 20 bucks a watt, 18 bucks a watt going in. Okay, so the question is, when do you get your money back? So from there, what I want you to do is, I think we can finish this up in 5 minutes, believe it or not. This is going to be cost of wind. This is going to be cost of geothermal equals dink. Okay, so that whole thing updated equals dink. I think I can take that. This might even work, watch. Yeah, so I just slid that over. It's pretty solid, Excel, thank you. Now, return on investment. Here's where we need to find the total energy, kilowatt hours. This is going to be kilowatt hours per year. number? No, no, no. Okay. Insert, shift and right. Okay, and this is going to be power AV in kilowatts. Equals that divided by 1,000. Let's not let it round quite so aggressively on us. Okay, now kilowatt hours per year equals kilowatts times 365 times 24 look out. Here's dollars. Actually, I've got dollars per kilowatt hour kicking around somewhere up here. I just got it at a dime. That's what it's going to, what it would cost you otherwise, kilowatt hours per year. And this is going to be dollars per year. So this equals kilowatt hours per year times dollars per kilowatt hour. Let's pin that. Pin that. Control 1. Number. No, no. Currency. Yep. Okay. So here's your payback. This is ROI. Let's just do this one for wind. ROI geothermal. ROI GT cumulative. So ROI wind equals, this is per year. Actually, the very first year is 0. This one equals that. And we're just going to assume energy prices don't change. If you want to get fancy and do some extrapolation, you know, you're welcome to. Equals that. And you know what? If carbon ever gets costed, the stuff's going to go through the roof. I mean, I can't even tell you how crazy renewable energy is going to get if someone actually puts a cost on carbon. It's going to go sick. Okay. Here we go. So these numbers, you can see this number is just adding the cell to the right times over the cell above. 0. So I grab this wind from the wind column. I'm going to 0 in your first year. This equals that number. This equals that number pinned. And then I think from here, I think I should be able to just take this whole thing, copy it, paste it, boom. Okay. Now, I think I'm done. I'm 1 minute over, but I'm pretty much done. The only thing left to do is I'm going to delete that, and I'm going to come in here and just plot the whole mess. Okay. So in this case, we have not yet broken even. What we're looking for, let's just look at the geothermal. There's your $120,000 system sitting right up there at the top. And here's your return on investment cumulative. Now, at 7 years, you're almost at 40K, which means your payback is going to be a long time. This is assuming, though, the cost of energy doesn't change. It's also assuming that we're not quite apples and apples here because we were looking at electricity. What you'd want to do instead is go back to that $10 per 1,000 cubic feet of gas and, you know, swap out the geothermal with the gas prices. But same exact calculation. But what that'll do, it'll give you a payback time. Same thing on the wind. Okay, you dropped your 50K right there. Your return on investment for wind is in yellow. And so at 7 years, you haven't really paid back, but maybe you will ultimately. Now, let's just say the price of electricity is 25 cents. Ooh, a little easier. Let's say we live on the island of Antigua, where they pay $1.25 a kilowatt hour. Now we're talking, okay? 2-year payback on the geothermal, and what we're looking at, 5.5-year payback on the wind. We actually ran these numbers in Antigua for a 1 megawatt array, and our payback was 3 months. And we got an email back from the premier saying, oh, no, sorry, won't work, can't do it. Sorry, no solar down here. Maybe a coconut will hit it and break it. We don't know, but we can't do it. Turns out, and I'll show you, this is online. Antigua Power. I think it's in the news. It might have even been that top article. But as it turns out, and I was able to research this a little bit, there's a Syrian who owns the power grid in yeah, I'm not going to be able to find it. 6 charged. Okay, so here's a little bit of news. This is new. This is since I've looked at it. Accepted 3 million in bribe. So these guys are paying $1.25 a kilowatt hour to have diesel fuel shipped in from the Middle East to run their lights. And as it turns out, the reason they said no, solar doesn't work is because the one guy who's getting all this $1.25 a kilowatt hour has his buddies bringing them diesel in from the Middle East, and then the money he makes off the consumers, he just sort of gives to the local government. There's your corruption to tell the renewable energy technology, no, solar won't work. Because if it did, you know, we'd make 20 million bucks worth of electricity, and the diesel crap would go away in a heartbeat, because there's plenty of sun in Antigua, for God's sake. So there's really no, what I'm trying to show you, I mean, sometimes there are financial barriers, sometimes there are technological barriers, but typically there are also political barriers too. So anyway, you don't have to get into that in your paper, but I just wanted to show you the sort of the ins and outs of the money. So hope does that kind of help get you along the way of, you know, comparing these qualitatively? Okay, and this will also pay off big time when you take 214, just working numbers and spreadsheets and converting from kilowatt hours to dollars. So thank you for your attention, and we'll see you Tuesday. Well, that was a long lecture. Woo.